Hello, everyone. I am Michelle Marine Corpus Garland from the College of Engineering. Today, I will present my research titled Application of Machine Learning Method for Predicting Material Cost of Portland Cement for Roads and Highways, which is item 311 from the DPWH standard. This study addresses the critical issues of cement price forecasting for road projects, especially item 311, which is widely used in highways. Before diving into the technical parts, I would like to emphasize that this research was conducted with support of MEO Bayombong and Nueva Vizcaya State University. Now, cement is the backbone of road projects. Yet, price forecasting is often unreliable. If cement cost is underestimated, government budgets fall apart. If it is overestimated, contractors inflate bids. Both scenarios leads to overruns, delays, and even disputes. This is why accurate forecasting is crucial. It helps balance risks between government and contractors. Now, machine learning offers a solution, unlike traditional trend analysis like guesswork. Now, machine learning can capture hidden relationships between cement prices, fuel cost, quarry proximity, and market volatility. The innovation here is not just prediction, but providing also an unexplainable and data-driven reference tool for engineers, contractors, and LGUs. So in short, smart cost planning for smart infrastructure. Our main objective is to investigate the feasibility of applying ML models, specifically random forest or RF, to predict Portland cement cost for item 311 in Nueva Vizcaya. To achieve this, we collected and standardized historical cement price data. And we also incorporated economic indicators such as fuel cost and inflation. We applied ML modeling and feature engineering, then evaluated performance using MAE, RMSE, and R-square. Our data came from three major sources: supplier quotations, contractor invoices, and government reference prices. We also added external variables like quarry proximity, diesel price index, and market volatility indicators. We use Random Forest Regressor in Python, Scikit-learn. Because this model is robust and handles nonlinear relationships and reduces overfitting. So evaluation was done with standard regression metrics, MAE, MSE, RMSE, and R-square, plus residual analysis to detect bias. Here, you can see an example of price fluctuations over time. The price range from below 200 pesos up to more than 270 pesos per bag. So such volatility highlights why simple averages or fixed reference prices cannot capture reality. And then, the research followed four main steps. Data cleaning, pre-processing, feature engineering like adding seasonality, inflation, quarry proximity. Number three, model training and testing. Number four is performance evaluation and interpretation. Our random forest model achieved an MAE of 9.38 pesos, RMSE of 13.22 pesos, R-square, which is equal to 0.35. This means, on average, predictions deviate by about 9 to 13 pesos per bag. The R-square of 0.35 suggests that while the model captures meaningful patterns, a large portions of variation is still unexplained. Predictions clustered between 220 to 270 pesos. The model underestimates low prices, less than 200 pesos, overestimates high prices, 270 pesos, greater than 270 pesos, and there is bias towards the mean. This happens because for extreme cases like rare price spikes or dips, which are not well represented in the data. And despite this, the model still serves as a useful first cut estimator, especially for planning purposes. Now, you might ask, why did the R square decrease when we expanded the dataset from 8,000 to over 9,000 records? So the possible reasons might be number one, data variability, whereas newer data captured more price shocks, inflation, or procurement changes. Number two, future limitations, which pertains to external variables like exchange rates, global supply chain disruptions, which are not included. Then number three could be the systematic bias, whereas random forest tends to regress towards the mean when faced with outliers. These factors explain the lower R square, but it does not invalidate the study. Instead, they reveal opportunities to refine the model. These photos illustrates the process, data collection and cleaning, converting qualitative features to quantitative, and then running my machine learning model and collaborating with municipal engineering office. This demonstrates the research was not purely theoretical, but grounded in real-world engineering practice. To conclude, machine learning proved feasible for cement cost forecasting in Nueva Vizcaya. Even with R square of 0.35, the model reduces reliance on guesswork and provides actionable first estimates. For improvement, we can recommend adding more economic drivers like inflation, exchange rates, supply chain data, hyperparameter tuning to avoid or reduce bias. Then we can also recommend to explore advanced machine learning models like XGBoost or CutBoost, then extending to other materials like steel, asphalt. Most importantly, this research contributes to risk reduction in budgeting, ensuring both government and contractors are better prepared for cost fluctuations. So despite moderate accuracy, this study shows the potential of AI-assisted forecasting. Rather than replacing human judgment, the model complements engineers and planners by offering a data-driven starting point. In the long term, this can support smarter, more sustainable infrastructure planning, not just in Nueva Vizcaya, but maybe across in the Philippines. So, thank you.